In case I didn't mention it, EET has got a lot of formulas which you must master, and they must be at your fingertips. So make sure you are able to write them down, and you are also able to solve some problems using those formulas. If you don't do that, then you will not make it in your electrical engineering technology course. So any worked examples in these videos, make sure you are able to get the correct answer. Once again, can you welcome me in the comfort of your homes as I bring Kirchoff's current law as well as Kirchoff's voltage law. You must be able to state these two laws and also to solve some circuit theory problems using them. Otherwise, guys, let us see. As usual, Motion Marfu is my name. Guys, don't forget to like, comment, or share, and above all, to subscribe. Learn at your own place, time, and pace as I bring Kirchoff's laws. These are simply two laws, Kirchoff's point law or Kirchoff's current law, and this is also referred to as Kirchoff's first law. Then the second law is known as Kirchoff's mesh law. Its popular name is Kirchoff's voltage law. Guys, you must be able to state this law, and also you must be able to use it to find current and voltage in any network. Otherwise, guys, let us enjoy our electrical engineering technology. This is what you must be able to do by the end of this video presentation. Number one, you must be able to state both Kirchoff's current law and Kirchoff's voltage law. Number two, you must be able to apply the two laws in solving DC network theorems. Then number three, you must be able to determine the total current by adding the branch currents. Then last but not least, you must be able to determine an unknown branch current. Otherwise, let us proceed to the nitty-gritties of Kirchoff's laws. We use the Ohm's law to solve simple circuits, especially those with one source of e.m.f. Ohm's law cannot be used to solve circuits whereby we've got two or more sources of e.m.f. or current sources. Kirchoff's voltage law as well as Kirchoff's current law are used to overcome the limitations of Ohm's law. Hence, the reason for this video presentation on Kirchoff's two laws. In this slide, we've got a point 0, and we've got currents flowing towards the point 0, and also some currents flowing away from point 0. For example, I1 is flowing towards, I2 towards, I3 towards, I4 away, and I5 towards. So we want to use this to define each of current law, and we can say we are using the algebraic sum, and we are saying those currents that are flowing towards the point 0 have got a positive sign as shown, and the current I4 which is flowing away from point 0 is with a negative sign, right? We can simplify further, and we are going to have I1 plus I2 plus I3 plus I5 minus I4 gives us 0. And if I4 crosses the equal sign, it is going to assume a positive sign. Hence, we can safely say I1 plus I2 plus I3 plus I4 must be equal to, I1 plus I2 plus I3 plus 5 must be equal to I4. It doesn't matter that I4 is only one current. So we are saying the algebraic sum of currents at this point must be equal to 0 as shown by this equation. Or we can say the sum of currents flowing towards a point, in this case 0, which is made up of I1, I2, I3, and I5. They must be equal to the sum of currents, which in this case is I4, flowing away from the point 0. So this is Kirchoff's current law, KCL. As I said, the term algebraic includes the sign of current or voltage. And if we've got 5 currents, I1, I2, I3, I4, and I5 meeting at a particular point, we may say those currents flowing towards a point have got a positive sign, and those flowing away from that point have got a negative sign. Hence, we can say the algebraic sum of currents at a point is equal to 0. Now, the second law, also known as Kirchhoff's voltage law, guys must be able to state is, and you can use the following statement. You can say, in any closed circuit of mesh or loop, the algebraic sum of all the voltages taken around is 0. Let's look at the validity of that statement. We are saying if we start from any point in a closed circuit and go right round and back to that point, there is no increase or decrease in the potential at that point. That is, the algebraic sum of all the voltages at that point is equal to 0. This means that, or you can say it in this way, the sum of all EMFs and potential drops around a closed loop is equal to 0. And we can assume a rise in potential as positive and a fall in potential as negative. So guys, you must be able to state Kirchhoff's voltage law using the algebraic term and also using the sum of EMFs and potential differences. What really are we saying? We are going to use the following concept in our analysis of Kirchhoff's voltage law. And we are saying, if we move from the positive terminal of the battery to its negative terminal, there is a fall in potential, and that source of EMF is assigned a negative sign. But if we move from the positive terminal of the source to its negative terminal, there is a rise in potential, so that EMF is assigned a positive sign. This also applies to potential difference. Please take note. And when a current flows through a resistor, there is a voltage drop across it. No current flow, no potential difference. And we are saying if we go through the resistance in the same direction as a current, there is a fall in potential, because we say a current flows from a high potential to a lower potential. So the potential difference will assume a negative sign. But if we go opposite to the direction of a current flow, there is a rise in potential, hence we assign a positive sign to the potential difference. So the sign of voltage drop depends upon the direction of current flow, and it is independent of the polarity in the circuit under consideration. Don't worry, this is going to stick when we do an example, so don't worry about that. More of KVL, and it can be stated as follows. The sum of EMFs around any closed loop of a circuit is equal to the sum of the potential drops in that loop. That's a good and more elaborate definition of Kirchhoff's mesh law, also known as KCL. And if you consider a rise in potential as positive and a fall in potential as negative, mathematically we can say the sum of EMFs minus the sum of potential drops is equal to 0, and mathematically the sum of EMFs is equal to the sum of potential drops, or you can say the sum of potential rises is equal to the sum of potential drops. It is correct if you are in an exam asked to state a Kirchhoff voltage law to use all these mathematical definitions. It's correct. So what we are saying insofar as Kirchhoff's voltage law is concerned is you must assume an arbitrary current direction for each branch current, and the end of the resistor through which the current is entering that resistor is positive with respect to the other end, meaning the other end is negative. And if you find a negative value of current, it means the direction of current is the other way. Can you take note of the following rule? A voltage drop exists when tracing through a resistance with or in the same direction as the current, or through a battery or generator against their voltage. That is from positive to negative. Please take note of that. So we are saying if we move from positive to negative when tracing through a resistance or through a battery or a generator, we have got a voltage drop if we move from positive to negative. An illustration of a potential rise and potential drop, and we are saying if we move from positive to negative, this is a potential drop or a fall in voltage, hence we assign it a negative sign. And if we move from negative end of one resistor to the other end, which is positive, then we've got a rise in voltage. The same applies to an EMF source. If we move from positive to negative, we say this is a fall in voltage, and if we move from negative to positive, we say there is a rise rise in voltage, hence we give that a positive polarity. So we are saying a voltage rise exists when tracing through a resistance against or in opposite direction to the current, or through a battery or generator, and we assign a generator with their voltage, that is from negative to positive. So if we move from negative to positive, we say there is a voltage rise. KCL worked a problem and find the unknown currents marked in Fig.14a, and the currents that we want to find out are I1, I2, I4, I3 and I5. So we'll start with I1. 50 amps is flowing towards B, 20 amps is flowing away from B, and I1 as well is flowing away from point B. So the sum of 20 plus I1 must give us 50 amps. So it means that I1 is equal to 30 amps as shown. Let's go to I2. This is I2. And what are we saying? We are saying 20 amps is flowing towards point C and 15 amps as well, which means I2 must be equal to the sum of the two. Hence, I2 is equal to 35 amps. We said current flowing towards a junction is equal to the current flowing away from that junction. Let's go to I3 using the same principle. This is I3. We said I1 is equal to 30 amps, and the current flowing away from D is 120. So it means that I3 plus 120 must give us I1. So what is our I1? Sorry. What is our I3? I3 is equal to minus 90 amps. And please take note that it means that the current is in the opposite direction to the one shown. So it means that I3 is flowing in this direction. Let's go to I4. This is I4. And we are saying it is flowing towards E. I3 is flowing towards E. So it means this plus this must give us 15 amps. Hence, it means that I4 is equal to 105 amps. Then the last one is I5. I5 plus 40 amps gives us 120. So I5 becomes 80 amps. So guys, this is how you solve Kirchhoff's current law problems. A current flowing towards a junction is equal to current flowing towards a junction is equal to current flowing away from that same junction. Another problem on Kirchhoff's current law. This time you are given a circuit diagram with two sources E1 and E2, and we said that you cannot solve this using Ohm's law. So the question says use Kirchhoff's laws to find the currents flowing in each branch of the network. This is Kirchhoff's current law, and it's a procedure I described for you to follow. Use Kirchhoff's current law because the question does not state, and label current directions on the original circuit diagram. So it's labeled I1, which is this current, I2, which is this current, then I3 is the sum of I1 plus I2. A current flowing towards a junction, I1 and I2, if you add them, they give you the current flowing through this branch. Then the direction chosen are arbitrary, but normally we assume conventional flow of current from positive to negative, as you can see. So there are two loops, this loop as well as this loop, assuming current flowing from positive to negative. Then let's proceed to the next slide to see how this was solved. Worked problem on Kirchhoff's voltage law, and it reads, determine the value of e.m.f. E in Fig.14b, and this is E that we must find out. So we want to apply Kirchhoff's voltage law, and we want to move clockwise around the loop starting from point A as shown, which means you have to choose an arbitrary point and direction. So we are saying in terms of voltages, we are saying 3, or in terms of e.m.f. rather, 3 plus 6 plus E plus, sorry, we are moving from negative to positive. So this is a potential rise, potential rise, potential rise, but this is a potential drop. Hence, we have got minus 4. So we are saying 3 plus 6 plus E plus C. E is a potential rise minus 4. This is the summation of e.m.f, and it must be equal to the summation of potential drops. Potential rise is equal to potential drop. How do you find PD? Is current times resistance. So we are starting from A. So we'll say 2 times I plus 2.5 times I plus 1.5 times I plus 1 times I. So we are saying the sum of e.m.f is equal to the sum of potential drops, and our I is given as 2. So we are going to simplify this side since we've got all values. So the sum of potential drops is 14. Hence, if we simplify this side, we are going to have 3 plus 6, that's 9. 9 minus 5, 4. So 5 plus this E must be equal to 14. The sum of potential rises must be equal to, or is equal to, the sum of potential drops. So our E becomes 9 volts. Guys must be able to solve Kirchhoff's current law as well as Kirchhoff's voltage law problems. Another worked problem on Kirchhoff's current law. This time you are given a circuit diagram with two sources E1 and E2, and we said that you cannot solve this using Ohm's law. So the question says use Kirchhoff's laws to find the currents flowing in each branch of the network. This is Kirchhoff's current law, and it's a procedure I described for you to follow. Use Kirchhoff's current law because the question does not state, and label current directions on the original circuit diagram. So it's labeled I1, which is this current, I2, which is this current, then I3 is the sum of I1 plus I2. A current flowing towards a junction, I1 and I2, if you add them, they give you the current flowing through this branch. Then the direction chosen are arbitrary, but normally we assume conventional flow of current from positive to negative, as you can see. So there are two loops, this loop as well as this loop, assuming current flowing from positive to negative. Then let's proceed to the next slide to see how this was solved. The next procedure is you divide the circuit into two loops, 1 and 2, and apply Kirchhoff's voltage law to each loop. And as we can, E1, which is the first source, this is the sum of e.m.fs in loop 1, and we are saying this is equal to the sum of two voltage drops, I1, R1. This is the voltage drop across R1, and I1 plus I2 times R. This gives a voltage drop across R when you are in loop 1. Then if we put some values, we are going to end up with this equation. 4 volts is equal to 6I1 plus 4I2. Then let's go to loop 2, and this time we are going to move in an anti-clockwise direction following conventional flow of current. In loop 1, we proceeded in a clockwise direction. As I said, the direction doesn't matter. And we are saying source number 2, E2, is equals to I2 R2 plus the sum of I1 plus I2 times R. And if you simplify, you are going to end up with another equation. 2 is equal to 5I1 plus 4I2. So we now have two equations, 1 and 2. And we say 1 and 2 are simultaneous equations that can be solved to give I1 and I2. So we are now going to solve two simultaneous equations so that we get the value of I1 and I2. Let us proceed. Guys, if you haven't subscribed, don't forget to do so. Guys, since this is not a presentation on simultaneous equations, I will leave that to solve or to prove that I2 is equal to minus 0.286 amps and I1 is equal to 0.875 amps. And what is the meaning of minus? The minus sign shows that the direction of I2 is opposite to that chosen. Let's find the current through R. It is the sum of I1 and I2, and if you solve the 2, you get 0.571 amps. Guys, Guys, this is how you should solve the given problem. You must understand your Ohm's law and as well as Kirchhoff's current law and a bit of your mathematics insofar as simultaneous equations are concerned. This time we are going to see how Kirchhoff's voltage law is used to solve a given problem. And we are saying you are required to find Vx and you are given two sources, e.m.f of 12 volts as well as an e.m.f of 8 volts. Guys, this must not confuse you. The negative sign is the same as the ground in this circuit diagram. So no need to worry about this. And we are going to proceed in a clockwise direction. So this is a potential rise, a potential drop, and also a potential drop. Hence, you are going to say 12 volts minus Vx minus 8 volts give us 0. So it means your Vx is equal to 4 volts. Simple. You add the sum of potential rises and it must be equal to the sum of potential drops. So simple. Another worked problem on Kirchhoff's voltage law. This time we've got a circuit, and this is the circuit, and we are required to find Vx. This is very, very simple, and we are going to form Kirchhoff's voltage law. We are going to say, we are going to choose this loop. 32 volts minus 12 volts minus Vx give us a 0, and you see that your Vx is equal to 20 volts. Or you can go it this way. Vx, you choose this loop, and you are going to say Vx minus 6 volts minus 14 volts is equal to 0. So your Vx will be 6 plus 14, and that is 20 volts. Let's proceed to the last problem on Kirchhoff's voltage law. We have come to the last solved problem on Kirchhoff's voltage law. This time we have got a circuit with one source and 3 resistors. And we are asked to find V2, I, R1 and R3. And guys, this is very, very simple. Once you know the voltage across, safely find the current flowing through it. Hence, V2 is equal to 54 volts, assuming an anti-clockwise direction, minus 18 minus V2 minus V3 is equal to 0. So your V2 is 21 volts. Then once we know that V2 is equal to 21 volts, if we divide that by 7, we get I, since this is the same throughout this circuit. So your I is 3 amps. And R1 is this resistor. So we know 18 volts is the voltage drop across it, and the current flowing through it is 3 amps. So the value of R1 is equal to 6 ohms. That's 6 ohms volts. Correct. R1 is equal to 6 ohms. R3, 15 volts divided by the same current, 3 amps, you get 5 ohms. So guys, I think insofar as the objectives are concerned, this is done, achieved. Go through the presentation, do the problems yourself, and you are done insofar as Kirchhoff's two laws are concerned. The first law and the second law, KCL and KVL. Guys, let me remind you, if you haven't subscribed, don't hesitate to do so. Also, you can like or comment, and don't hesitate to share.